Hi, everyone, and thanks for joining us today for episode 708 of People Behind the Science. I'm your host, Dr. Marie McNeely, and in our episode today, we are revisiting our interview with Dr. Charles Hohenberg, originally published on June 19th of 2015. Listeners, Charles uses mass spectrometry to study noble gases like Krypton and Xenon in sources such as meteorite samples to answer a wide variety of scientific questions. He designed and built his own mass spectrometer, which is one of the best in the world. And in our interview, Charles shared great stories about his life and research. So listeners, get ready to learn more in this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of People Behind the Science. I am excited to be here today with Dr. Charles Hohenberg. So welcome to our show, Charles. How are you?
I'm very good. Thank you.
Wonderful. Well, we are delighted to have you on the show this morning. Now, listeners, just a little bit about Charles. He is a professor of physics at Washington University in St. Louis. He received his PhD in physics from the University of California, Berkeley, and has been on the faculty at WashU since 1970. Now, Charles has received many awards and honors during his career, including election as a Fellow of the Meteoritical Society and a Fellow of the St. Louis Academy of Science. He has also been awarded the NASA Principal Investigators Award, the NASA Exceptional Achievement Award, and recently the James B. Eads Award honoring engineering or technology from the St. Louis Academy of Science. And listeners, Charles is here with us today to tell us about his journey through life and science. So Charles, today we want to get to know you, both as a scientist, but also as a person. So can you start off this interview by telling us what you like to do with your time when you're not doing science?
I'm a born tinkerer. I think one of the things about an experimental physicist, which is the kind of physicist that I say does hands-on work, I do hands-on work around the house, all the plumbing, woodworking, electrical work. I do that both in the laboratory and at home, so I enjoyed that.
Wonderful. Well, next time something goes wrong in my house, I know who to call.
Okay.
That is phenomenal. I know I myself am a bit of a do-it-yourself or home improver myself, so it's a lot of fun, and it's nice to see the finished product after you work on it, which I think is the best part. So what is the most recent project that you've worked on in your home, Charles?
Actually, my son and I just finished building him a deck beside his house with a built-in hot tub. I'm a woodworker by hobby, and I've built our own kitchen table and a kitchen table for my son and a coffee table and numerous other things that I've done.
Fantastic. Well, great to hear about what occupies your time when you're not busy in the lab. But next, Charles, I want to know about your science. Can you tell us how you describe what you do to someone who might not be familiar?
Well, you might think it's a very specialized field that I'm involved in. I do mass spectrometry of noble gases, that is the inert gases. And it's interesting because inert gases are often called rare gases because they're so depleted in nature. But because they're inert, they don't react with other elements, which means they're very, very easy to purify, so you can study these very well in a mass spectrometer. And because we have those special needs of measuring these special elements, the noble gases, I designed and built my own mass spectrometer. And the one we're using now, which is currently the best one of its type in the world, I built when I was on sabbatical in Switzerland back in 1975, and we've been using it ever since. So I design and build my mass spectrometers and use those to measure noble gas isotope ratios. Now, isotopes are the same element, but different isotopes in different masses by the number of neutrons they have in the nucleus. So we can separate the different isotopes with the mass spectrometer. That's what it does. And I'll go and give you the detailed applications of that. But what we do is measure noble gas isotope ratios from various sources. And this is a unique way and very enlightening way to find out about different processes. And what we study primarily are samples of the early solar system, mostly meteorites, because meteorites never went through planet-warming processes. They're well-preserved samples of the primitive solar system. So by studying those, we can get a sample of the pristine early solar systems in our laboratory to work with. That's what I do.
Very interesting. So do you get to collect the meteorite samples yourself, or do you just process what people send you?
I process what people send me. I haven't done this because I've been too busy in the lab, but one of the interesting places to collect meteorites these days happens to be the Antarctica because it's a continent. Unlike the Arctic, which is not a continent, there are mountain ranges in the Antarctic, and the snow falls on the South Pole. It stays there forever because it's always cold, but the more the snow falls, it extrudes itself over these mountain ranges and ridges as it goes northward. And as the snow extrudes over the top of a mountain range, the wind ablates the snow away. Well, if any meteorites happen to fall with the snow in that region of the Antarctic, as the glacier, you might call it, extrudes over the mountain range, the wind ablates the snow and ice away, and there perched on a little ice pedestal will be a meteorite.
Oh, wow.
And so by taking helicopters and snowmobiles over the Antarctic, you can pick up thousands of meteorites. And a lot of my colleagues have done this so many times. It's a lot of fun and brings a lot of new meteorites into the laboratory.
Well, that is phenomenal. And Charles, I'm looking forward to chatting more about your research as we go through the interview. But let's back up a bit and chat about motivation. I love getting little tidbits of motivation and inspiration from everyone I talk to. So can you share with us one of your favorite motivational quotes?
My favorite motivational approach, I think, is just scientific curiosity. Why is this way? And when you lie out on the blanket on a warm summer night and look at the stars, what is that? How did that all come to be? And how can there be so much order in a seemingly chaotic universe? I think that curiosity and that motivation spurs on a lot of scientists, I feel.
Absolutely. And definitely taking that step back. You know, I think we get so entrenched in the detail of the work that we're doing. Sometimes it's good to take a step back and really appreciate and be curious and have that sense of wonder.
Oh, yeah.
So, Charles, great to hear about this motivating force. And next, I want to hear about some of the people who have motivated or inspired you over the course of your career. So can you tell us about a role model?
Well, my role model was my research director when I was a graduate student at the University of California, Berkeley. His name was John Reynolds, and he was kind of the father of noble gas mass spectrometry in the West. He really invented that. And I have a colleague who I didn't know, but I knew of his research director in the Soviet Union. His name was Yuri Sukholyukov. And I had heard of Yuri's work, and I had gotten Yuri's work. In fact, once Yuri came and visited my lab at Washington University, got to meet him. And back when we were needing a scientist to come and help, a postdoc scientist, the Soviet Union was having difficulty, and some of the scientists were getting restive in the Soviet Union. I asked a friend of mine who actually had hired Yuri Sukholyukov's son to work in his lab. He worked at the University of California, San Diego. He put me in contact with a fellow by the name of Alex Mishik in the old Soviet Union, who was a student of Yuri Sukholyukov. And Alex came to my lab 19 years ago. His wife came along, so we've been working as a team since then. And we were born on opposite sides of the globe, but our interests, or so I'd say we could have been brothers. And he was the person that has influenced a lot of my research.
Wonderful. Well, I love that you brought up this aspect of science as being so international. And I think this is a story a lot of people tell with forming these close collaborations with people maybe across the globe in different countries. And I think that's really one of the great parts about careers in science. So how did this international collaboration, you told us a little bit about it, how it started. So how has that shaped your lab?
I think you tend to get myopic in your own research and your own research directions, and it's nice to work with somebody who has a totally different point of view, different talents, and it's kind of like being family members. You discuss things and compromise and come out with something better than either one of us could have done alone.
Definitely. Well, Charles, I'm curious to hear about where your passion for science started. We've chatted a little bit about your journey and the people who've inspired you over the course of it, but take us back to the beginning now and tell us where it all began.
I guess it began at my home. I was born in Alabama, and a couple of friends of mine and I like to build things. And so when I was about, 12 or 13 years old, we decided to build this ramjet engine in the backyard, which was just a stovepipe with a piece of copper tubing inside. We put gasoline in. It's lucky we didn't burn ourselves up. But I actually went from public high school to a private high school near Birmingham called Indian Springs School, which was a good college preparatory school. It was just a brand new boarding school that started in Alabama, one of the first, and I was one of the first graduating classes. And when I was at Indian Springs, my shop teacher there had his pilot's license, so I learned to fly and eventually became the treasurer of the flying club at Princeton University. I went to Princeton as an undergraduate. So I went in first into mechanical engineering because I like mechanical things, but I didn't really like the idea of designing bridges and things. And so I then went aeronautical engineering, but that wasn't a field where you could really understand something, because aeronautical engineering was somewhat of an art as opposed to a science, because the flow of air over surfaces was something that was difficult to describe. And so anyway, I liked my physics course then as an undergraduate, so I became a physics major. I really liked my undergraduate physics teacher. His name was Jerry O'Neill, and he went on to establish a planetary society about what to do when the Earth is overpopulated. How do you migrate to space? He encouraged me a lot, and so then I went from there to Berkeley. I had done some mass spectrometry work working in the summer for Jerry O'Neill at Princeton. And so when I wandered into Berkeley looking for work to do, I thought I wanted to do cosmic ray physics, but they were full. But then I just needed a job, and I saw this sign on the door that said mass spectrometry. I said, hey, I know how to do that.
I could try that, yeah.
So I wandered into the lab, got a job, and the rest is history.
Wow, that is phenomenal. I love these chance happenings that scientists describe that really paved the way to their careers. And now you mentioned as a child, you were really interested in kind of tinkering, building things, and this is something that has continued on today.
Right.
Did you have a scientist to look up to, or were there other inventors or tinkerers around you? Were your parents perhaps encouraging this hobby?
My uncle was a scientist, and I got a lot of inspiration from him.
Okay.
And one of the other things we used to do, in addition to building a model ramjet in the backyard, my grandmother had type 2 diabetes and lost her vision and couldn't drive, so I inherited her car when I was 16. So I ended up putting a spark plug on the exhaust pipe and a Model T Ford coil to power the spark plug in the truck and a switch on the dashboard. And so whenever I was going down the highway, I could flip the ignition switch off, turn that switch on. I get this big blue flame going out my exhaust pipe. I thought that was pretty cool.
Oh, wow.
So that's the kind of thing that I did as a kid.
Oh, that is phenomenal, Charles. Wonderful to hear a little bit about your own history and your path to get to where you are today. But next, I want to talk a little bit more about these projects that you're working on today. Can you share one with us in detail that you are the most excited about?
Well, let me just tell you a couple of things that we do. Noble gas mass spectrometry, as opposed to a scientific field, is a technique that you can use in a lot of different areas. In particular, you can change the isotopes of the noble gases, and the most important one is xenon, because it has 9 isotopes. It's very depleted in nature, so you can study a lot about the world around you by looking at the xenon isotopes that happen in a particular process. One of the things that we did, and both Alex and I did this independently on opposite sides of the globe, there's a uranium deposit in Africa, in Gabon. It's called the Oklo deposit. And it was explored by French who were looking for places to mine uranium for their nuclear program. And they did the isotopic ratio and said, hey, there's not enough U-235 in here. Where is that? Because the ratio of U-235 uranium to U-238 is constant worldwide. And it turned out the reason there wasn't enough U-235 is because this uranium deposit had a high enough concentration of uranium. And 2 billion years ago, the ratio of U-235 to U-238 was high enough to be a natural nuclear reactor. Now, what the Iranians are doing and other people are doing to make fuel for reactors is enrich uranium and make more U-235. Well, nature did that for you because U-235 half-life is shorter than U-238. So back earlier in time, there was a higher percentage of U-235 in uranium ore. Well, this particular ore deposit had enough uranium to be a natural critical mass of uranium that started a self-sustaining nuclear reaction. In other words, it was a reactor in nature that occurred 2 billion years ago.
Wow.
And we were worried about what happens when there's a nuclear disaster and a reactor content gets exposed to nature. Well, this was in nature.
Right.
It was out in the open. And in fact, what made it work, you've heard of water-moderated reactors.
Yes.
The neutrons that come from fission go so fast, they're not easily captured by another uranium atom nearby. They have to slow down. Well, water naturally slows down neutrons. And this uranium deposit happened to be in an environment where there was a lot of water. And so when the water was present, the neutrons slowed down and it made a natural chain reaction. But then it got hot because it generates a lot of energy. So when the water gets hot, it flashes into steam, and because there's no water left, the reaction shuts down. So it's called a pulse reactor.
Interesting.
That may sound curious and strange, but we make those today. They're called trigger reactors, and we have one in University of Missouri-Rolla. We have a trigger reactor, which does exactly the same thing. You have water present. When the reaction takes place, it heats the water evaporates, it shuts the reaction down, so it pulses. And you can get high-intensity neutron bursts that way to study. And this is what happened in nature 2 billion years ago.
Wow.
That's one of the projects we do.
So is the only known one, this one in Africa that you're describing, or are there other ones?
We looked for another one, not that extensively. We looked at an old Canadian uranium deposit that was 1.2 billion years old, but we didn't see any evidence, and there really hasn't been a complete worldwide survey. But this was like 25 years ago we did that.
Gotcha.
And there are a lot of different things we do. The most important contribution we made really was we can study by the xenon isotopes the evidence of radioactivities that are now extinct. They don't exist in the solar system anymore because their half-life is so short and they were created in supernovas nearby before the solar system formed. And one of these is plutonium-244, which we studied in meteorites for the last 50 years or so. Another is iodine-129, which has a 17 million year half-life, and that decays to xenon-129. And the interesting thing about that is we can use the iodine-129 as a dating scheme. We can date the formation processes with high accuracy in the early solar system. And Alex's wife, Olga, that's what she does all the time. And this is probably the most important contribution that we have made is developing the iodine-xenon dating scheme into one that can be reliably used to study the early solar system. And there are lots of other things we do. We use Krypton. Mm-hmm. It's not just for Superman, it is also for measuring things in the solar system. Krypton dating is a way we can use cosmic ray-produced radioactive krypton and stable krypton in lunar samples to date when those rocks were brought to the surface to be exposed to cosmic rays. That's dating the ages of lunar craters. We've done that on the returned lunar samples. That's also using our mass spectrometer.
Well, very interesting. I know many of our listeners might be familiar with carbon dating. Is the concept similar behind it, except you're just using different isotopes?
It's similar in the sense that radioactivity is the clockwork mechanism for both. Now, what carbon dating does is carbon-14 is formed in the atmosphere also by cosmic rays, and of course it is incorporated in carbon dioxide. And trees breathe in this carbon dioxide and convert it into carbon as part of their cellular structure and that sort of thing. So it reflects the carbon-14 to stable carbon-12 ratio that's around when the tree lived. Once the tree goes down and becomes a coal or a fossil or part of you and me, it's cut off from the atmosphere. So any carbon-14 which are radioactive in that organism or in that tree or in that fossil, it decays. And so by measuring the ratio of carbon-14 to carbon-12, stable carbon-12 that's in that fossil or you or me or something like that, it's a piece of wood, you can determine how long ago that piece of wood died. That is, that piece of wood was cut off from the atmosphere. That's how carbon dating works. The way iodine-129 dating, iodine-xenon dating works is when the object in the early solar system formed, there was iodine-129 still present. And iodine-127, the kind we find that's added to salt and things, the kind we have now, that's stable. Mm-hmm. So the ratio of iodine-129 to iodine-127 at that point in time might have been something low, like 10 to the minus fourth or something like that. 0.0001 would be the ratio of 129 iodine to 127. Once you form a rock, that iodine-129 decays to xenon-129, which we can measure. So you have the mechanism of measuring the accumulation of iodine-129 to tell you when that event occurred. But it's actually easier than that, because we can take the meteorite sample and put it in a nuclear reactor and convert stable iodine-127 by neutron capture into xenon-128. So all we have to do in the mass spectrometer is measure the ratio of xenon-129 to xenon-128, and we have inferred the ratio of iodine-129 to iodine-127, the first being radioactive, the second being stable. At that time, the solid material formed and was able to retain xenon. So we have an accurate date of when that closure occurred. And don't forget, the precision is like 10,000 years in something that happened 4.6 billion years ago.
That's so impressive. Well, Charles, this is phenomenal work and really interesting to hear more about your research, some of the projects you're working on. It really sounds like your research brings together chemistry, physics, and astronomy. Was this a challenge, really working in such an interdisciplinary field?
It's fun. It really is. A lot of people are geologists, a lot of people are chemists, and a lot of us physicists. I think we're physicists are in the minority, but we actually come through with the equipment and with the innovations and the way to irradiate samples to produce the effect we want. So I think we contribute a lot, but it's a lot of fun to work with everyone. And what's interesting is the people that study meteorites have this organization called the Meteoritical Society that covers all scientists of all fields. We're just interested in studying the early solar system through meteorites. And the interesting thing is half of the members are European and half of them are from this hemisphere, this continent. And so when we have meetings in alternate years, we have them in every country on the globe that host these. So we get to see scientists of all over and work with them closely and see them once a year one way or the other. And that's what makes it fun.
Absolutely. Well, wonderful to hear more about your work. And Charles, I think so far we've talked about a lot of the high points in your career, the great things that you've done and been able to work on. But I know every scientist faces challenges and has dark days or things maybe aren't going the way they planned. So can you take us back to one of these challenges or one of these failures that you experienced and tell us a little bit more about it? Just because I think so many times people just hear the success stories in science, and I think there's so much more to the story.
Well, I don't know if it's exactly what you talk about, but one of the things I think that makes scientists contribute a lot is the attitude a scientist had. And I think one of the characteristics of a good scientist, what I would call is scientific arrogance. In other words, he knows his capabilities, he got the training, and he's not hesitant to apply his skills to any field he wants. He's able to look at all fields and apply his talent wherever he can, and that's a healthy attitude. But I think more important than scientific arrogance is scientific humility. That is realizing that the world around him is something so much more complex than he could ever imagine, that he only brushes the surface. Just as an example, I taught an astrophysics course when I first came to Washington University, and we knew all there was to know about the universe.
Of course.
We knew how stars formed, how the elements that you and I are made of were created. We knew when the sun was born and how it was going to live and when it was going to die. We were about middle-aged through the sun. It'll die in about 10 billion years in the future. We knew all of that. We knew that gravity attracts matter, and so we knew from Hubble's law that the farther something is away from us, the faster it's receding away from us. But we also know from Newton's law that matter attracts other matter. And the only question that scientists did not know about the universe, the only question they didn't know, the only one that they were really working on, they knew everything else, was whether the universe was open or closed, whether there was enough matter in the universe, slowing mass down as it expanded, so that that mass eventually stopped and maybe fell back in for another big bang, or whether the matter would keep on slowing down but keep on accelerating forever. That was the open universe. The former was the closed universe. That was the only question that needed to be answered. The last course I taught at the university was an astrophysics course, and in the intervening years, we had discovered that dark matter existed. From the rotation rates of galaxies, you can see there's much more there in the galaxy than meets the eye. In other words, it's not just stars and gas and all. It's something we can't see. It's in there. We call that dark matter. And then when Hubble cranked up its carefully calibrated eyes, it could see farther than they could see before, and we could measure the redshifts of galaxies that were receding from us, and we could measure them over time, and we could determine how the universe was slowing down. Once and for all, determine whether the universe was open or closed. Well, the answer was what we never expected. The universe is not slowing down. It's speeding up.
Right.
There's something in the universe that's pushing matter apart. It's not just slowing down like gravity would have it. And we call that unknown thing dark energy. So we have two unknowns that we didn't have before, dark matter and dark energy. And between those two, they account for 97% of the universe. So what we were so confident in knowing it all, we've realized we only know 3% of the universe. And that's what I call scientific humility. That's what we need more of. And we need to realize that the joy of science is not in the result we get, but in the journey toward that result, because that result may not be what we expect. We learn more along the way.
Well, Charles, what a great story. I think you brought up so many important points there. And I really like thinking about these major shifts in what we know and what we think we know, what we realize we don't know about the world. And it sort of rewrites the textbooks in a variety of different fields. These things have happened. So great to hear about your experiences. Now, has this been a challenge then in terms of going back to looking at your old lectures and thinking, all right, well, we have to rewrite everything this year?
Well, one of the things I told my class, I taught the mainline pre-med physics course for like 20 years or so, 25 years over my course of teaching at Washington University. But what I always told my class was, the first day of class, I said, there are no laws of physics. They're just mathematical descriptions of observations we make. They're just describe nature as we see it. Once we can see nature with a little more detail, we're going to have to change those laws. They're a lot like the laws of speeding. If you violate the law, there are consequences. In physics, if you violate the laws of physics, there are consequences. The consequences are simply that you have to rewrite the laws. And we do that all the time. We went from Newtonian physics to relativity. We went from classical physics to quantum mechanics, just because we realized that we can't explain nature to the detail that we've been observing it by the laws we already knew. We have to rewrite those laws. And so I like to think of the universe as something scientists learn about. It's always an eye-opening journey that we make. It's sort of like if you were an art student wandering in an art museum and you've studied art all your life and you see this work of Rembrandt and you can analyze every brush stroke he made, how he got this effect, how he got that effect. So you're looking at this work of Rembrandt, and you can fully appreciate that. And the more you study, the more you appreciate it. But you're not the artist. You never could be a Rembrandt. You can only study and appreciate his work more. And that's what I feel about science. The more we learn, the more we appreciate nature. We can't make nature. We're not responsible for making nature, but we can certainly understand it and appreciate it. And that's the beauty of science, in my opinion.
Definitely. And there's no way to go back to the beginning to see how something was originally made. You just sort of have to take the clues that you can find and piece together what you think happened. I think is also a really interesting part of science, is being able to put together that puzzle to guess at what happened those millions, billions of years ago.
Right. And you can appreciate it. The more you understand, the more you appreciate the beauty of it all. And again, I'd say the way you can really appreciate the beauty, and you and I can do the same thing, is put a blanket out on a warm summer night and look at the sky. The beauty is right there.
Absolutely. Well, Charles, wonderful to hear about the evolution of knowledge in your field and how that has caused some challenges, some rethinking of what we know about the world and how we think about it. And next, I want to talk about a success story. So, Charles, I know you've had many successes in your career. Can you share one of these stories with us today?
One recent thing we did, there was a mission. My colleague, Don Burnett at Caltech, is a principal investigator of the Genesis mission. And the Genesis mission was a spacecraft that was launched in 2002, I think, that went to study the solar wind. Now, why would you want to study the solar wind? It parked itself in one of the Lagrange points, which is a gravitationally stable point, for 2 years, sampling the solar wind. It would sample the normal solar wind. It had panels that would come out whenever there was a solar flare and sample that. It was a spacecraft that was just designed to learn as much about the solar wind as we could. Why do we want to learn about the solar wind? It's because the sun contains 99.9% of the matter of the solar system. So if you want to see how the solar system began, the elemental ratios that we see on the moon, the earth, and that sort of thing, it started with the sun, because the sun contains 99.9% of the stuff still. So that's the starting material. So in order to understand the solar system, we need to understand the material from which it began. Well, you might know the Genesis mission followed on the heels of another mission that I was involved in called Stardust, and it was built by the same company, and they put a lot of the same equipment in these two spacecraft. Unfortunately, when they put the accelerometer, the switch that deployed the parachute, on the Genesis mission, they used the same switch that they used in Stardust, and so they didn't have to test it. They knew it worked, but it was mounted backwards.
Oh, no.
In the Genesis mission. To make a long story short, the parachute never deployed, and it hit the Utah desert at 200 miles an hour.
Wow.
The amazing story is almost all the scientific objectives of that mission were recovered from those pieces in the Utah desert. And we actually have much better results than we ever thought we could, because technology in those intervening years actually improved. So we did a lot of the work on the heavy noble gases and all the noble gases that came from the sun. And from that, we can understand better how the noble gases and meteorites formed and what they look like, and understand better the evolution of the solar system. That was one of the recent successes. It's like a phoenix rising out of the broken mass of the mission, and we actually accomplished more than we thought we could from that.
Sure. So what is it like then? Is there a lag between when the information gets to NASA versus when it gets sent to you, or how does that work in terms of being a part of this team?
Well, we actually know what we can do, and we know what the collectors are there on the spacecraft, and so we request different material. We talk about it with other scientists and all of them, and they get sent to us, and we put them in our instrument measure.
Gotcha. Well, very cool to hear about one of these successes in your field. And I think coming especially after this sort of heart-wrenching catastrophe where it crashed into the Utah desert, as you're describing. So
right.
How did you feel, or what were the thoughts going through your head when you heard the bad news and then were able to get the good news later?
I pessimistically thought, well, it was perfect right up until the end, and now it's gone. That was too pessimistic. We got to be optimistic in our view about the future. And indeed, we were able to pull victory out of defeat. That was great.
Gotcha. Well, phenomenal story, Charles. And we chatted a little bit about your work that you've done over the course of your career and a little bit about the things that you like to do when you're not at work. And I think one of the things that scientists cite often as something they like to do to escape from science is to read a little bit for fun. And we haven't yet chatted about what you're reading today, Charles. So can you recommend for myself and our listeners a book that you've really enjoyed that you think we should check out?
I just happen to be reading a book, and this may not be politically correct, but it's kind of fun to see how science works. It's a book by Richard Rhodes. It's about the discovery of nuclear fission, and it was a long, slow process, and it's got so many historical facts in it. I'm reading that, and I'm enjoying that right now.
Well, excellent recommendation. I'll put that out on our website for our listeners to find if they're looking for their next good book. I know I'm always adding things to my list, so perfect. And we've chatted a little bit about different places that you've traveled for different opportunities in science, either for training or different conferences and things. And I think this is one of the really great aspects of the career that maybe people don't realize, that you do get to do quite a bit of traveling to share your science, to work with scientists all over the world. Can you think back now on all the places that you've been for science, Charles, and tell us about your favorite place?
Well, I'll tell you a place I didn't go that I really feel like I probably should have.
Sure.
And as I mentioned, the collection of meteorites from the Antarctic. I sent a lot of my students there, but I thought maybe between teaching and the research I was doing in the lab, I just couldn't take the time off. You have to spend 2 months there. But a couple of my students went on 2 trips there, 2 seasons, and they love it. And it's a landscape that you won't forget, and driving your own snowmobile and picking up meteorites and cataloging those. And since it's hard to take food into the Antarctic ice fields, you have to carry everything. There was no limit about what people could take in terms of food. So it was fillets and lobsters and all that sort of thing.
Oh, wow.
They ate well when they were there and enjoyed themselves, and I was kind of jealous about that. But I've enjoyed all the countries I've visited: Australia, New Zealand, France, of course, Germany, and Ireland, India, Czechoslovakia. I've enjoyed all the places we've had our meetings. One I didn't go to that I probably would have enjoyed going is Brazil, Rio de Janeiro. We had a meeting there. But you get such a good chance to visit other parts of the world and interact with scientists and graduate students who probably wouldn't be able to travel to your country. So you get to interact with them in their own environment. That was nice.
Definitely. So is Antarctica in your future, Charles?
I probably won't go. I think it's funded by the NSF. I think money for science is, like everything else in the U.S. budget, is under scrutiny, and I just think that program, if it survives the next few years, will be great, but I'm not going to occupy it myself. Let the students go.
Gotcha. Well, wonderful to hear about some of the places that you've been. So what's the most recent trip you've taken?
I just recently took a trip to Australia. I gave a talk there about the mass spectrometer. I actually built the new mass spectrometer when I was in Zurich in 1975 that developed, and I gave talks about mass spectrometry in Australia. That was probably the most recent.
Wonderful. So do you tend to be the more in and out type traveler, or do you like to spend a little bit of time there on the beginning or end of the trip to do some sightseeing?
It depends on what I'm doing. If I've got classes to teach and work to do, sometimes I don't have luxury of time, but there are always field trips and I always take a half a day or something like that. See the local scenery, we enjoyed that. But we had a Meteoritical Society meeting in 2001 in Rome, and we took 2 weeks off, rented a house in Tuscany, and just enjoyed the Italian communities there and the wine and the food, and that was fun. Strictly non-scientific.
Well, Rome is definitely on my list of places to visit. I've been to Australia, phenomenal country, been to a couple cities there, so great travel experiences that you've shared with us. And I think definitely important to highlight some of these opportunities that you get in science to travel, to see the world. And I think that is one of the things that's attractive about the career for a lot of young scientists out there. So we've talked a little bit about travel, and through this, we've mentioned some of the people that you've gotten to work with. And I think we mentioned specifically some of the scientists internationally that you've had an opportunity to collaborate with in your field. And I think these opportunities to work with a variety of different people with a variety of different perspectives is really important in science. And I think in science, scientists get some bad bad stereotypes. There's sort of the vision, I think, in the media of scientists going into their lab, having a very solitary pursuit, being sort of quiet, critical people. And I think that's not accurate in many, many cases.
It's not accurate. I think there are a few scientists that keep their cards close to their chest, but most scientists are open with their data, and it's not like you're jealous of other people. You just want to share what you've discovered and talk about it, and that cross-fertilization is very important in science, and the communication is very open, particularly between people in different countries. I mean, country boundaries totally disappear in science. You're just colleagues and friends.
Absolutely. And I love hearing stories about the human side of science and people working together and having fun together in science. So can you share with us, Charles, one of your own memories or maybe one of these traditions that you experienced working in a particular laboratory that really highlights the human and the fun side?
We had once in our lab, back before I built the mass spectrometer in Zurich, the mass spectrometer that John Reynolds started when I was at Berkeley was the glass mass spectrometer. We did all of our glass blowing ourselves, and all the tubes were made out of glass, and it was a very fragile instrument, and we were always afraid that someone would literally drop a wrench on the glassware in the laboratory for a total disaster. And we had, I'm sure the name is so common it won't matter, but we had a person that works for us that was kind of clumsy. He was a nice guy, but kind of clumsy. And literally, he did drop a wrench and broke the glassware and just destroyed everything. We had to start over again.
Oh, no.
And this is not a fictitious name, but it's common enough it won't matter. His name was Cary Smith. So from that point on, if somebody did something totally stupid, like left something on or forget to close a valve or miscalculate something, he would be awarded the Cary Smith Award for that week.
Oh, wow.
And we did glass blowing, and what we tend to do is you have cobalt glass, which is blue, and uranium glass, which is green, and regular glass, which is clear. And we do glass blowing for our glass system. So we would glass blow this nice kind of swan-like statue or something, and someone would come in, and they forgot to do something. They didn't even know that they forgot something. And they come into the office, and sitting on the desk was the Cary Smith Award. And they'd say, what did I forget to do?
Right.
So that's what we passed around from disaster to disaster, from things that overlooked other things. That was the funny part.
Well, that is awesome. Cary Smith, living down in infamy, I think. And I think that is one of the things that I love to point out in science is there's so much personality and people like to work hard, but they like to have fun too. And I think being so passionate about your work and working with people who are so passionate about it, you get these great laboratory environments. And I know having pulled even just little glass pipettes myself, it is a struggle. So that would have been devastating to have all the glassware broken. So Charles, wonderful to hear one of your fond memories in science. And I think we've talked a little bit about the work that you've done, but we haven't yet chatted about the big questions that are still in your mind to answer. And this is one of my favorite questions to ask scientists. Basically, the what if we gave you everything question. So Charles, if things like funding, staff, technology, feasibility, not an issue, what is the one question that you would want to answer?
There's so many questions that I want to answer. One of the immediate questions, scientific type questions that I would like to answer, finding out the composition of the sun, we can determine the composition that everything began the solar system with. We have an enigma because meteorites contain a reasonably large amount of these noble gases. And it turns out that there is a process that we can take a meteorite and dissolve it in all kinds of caustic chemicals and end up with a residue that may be 1% of the starting mass of the meteorite or less. And we can measure the noble gases in that, and we can find out that the heavy noble gases, xenon and krypton, it hasn't lost any. It's lost 99% of its mass, but it hasn't lost any of these noble gases. And then we can treat that with a highly oxidizing acid like perchloric acid, and you can't tell any change. And it hasn't lost any more mass, but it's lost all of the heavy noble gases. So there is a carrier phase, probably a two-dimensional film, that contains all of the heavy noble gases. And we call that phase Q, kind of the quintessence of the noble gases. Nobody knows what that is. It may be carbonaceous film because carbon is eaten away by these oxidizing acids. And it differs in composition from the initial starting composition of the sun, just like it's been fractionated. In other words, the heavy ones are more abundant and the light ones are rarer isotopes. And so the question is, how can you get the concentration? Now, the concentrations required of that phase Q are so high, we never see them in nature at all. The only place we've ever seen them are in these Oklo natural reactor samples that I talked about earlier. Mm-hmm. How do we get these high concentrations? And the answer that we discovered is there's a whole new process for noble gases. We think of noble gases as being inert, and they are. They don't react with other elements, and they don't really normally. But if there's nothing around, xenon has 8 valence electrons and it's big enough, it would like to have a friend. It would like to attach to something. So if there's nothing else competing with it, it will make chemical compounds. And what we discovered is that if you create free chemical bonds somehow, either by ionizing radiation, which happened in Oklo, by bombarding with particles, by irradiating with ultraviolet light, or even by breaking it in the laboratory, you create free chemical bonds, and the xenon will bond there.
Interesting.
And if xenon is bonding on the surface, it doesn't require a carrier phase. It's just a two-dimensional layer. So we think that's phase Q. It explains not only the composition of these so-called planetary gases compared to the solar, it also allows you to understand why they're so concentrated. In the Oklo reactor, the only other place in nature we've seen concentrations this high, because of the radiation environment, you do break chemical bonds, and you do let the noble gases chemically bond to the surrounding material, to the elements that happen to be there. The reason we don't see that in the atmosphere on Earth is because there's so many chemically active species in the atmosphere, oxygen, nitrogen, water vapor in the atmosphere. Anytime you have a broken chemical bond, those active elements get it, the noble gases don't. So we don't see this process much in Earth. So that is a breakthrough that's about to come, I think.
Very interesting. Well, fascinating to hear about one of these enigmas in your field that it sounds like you're pretty close to potentially solving, or at least solving until proven otherwise. But
well, we did some experiments back in 2002 to demonstrate this stuff that we call anomalous adsorption. It's actually chemical bonding. We did experiments there when we were preparing an experiment for the Stardust mission, but we got so involved with the missions, Genesis and all, that we hadn't really had a chance to pursue it. And I'm hoping that we'll find a postdoc or graduate students willing to take that up and pursue that process in the lab a little bit more.
Gotcha. Well, listeners out there, that sounds like an open invitation if anyone's interested.
That's right.
Fantastic, Charles. Well, I know as a scientist, you get fantastic advice throughout the course of your career, and we love sharing this advice with our listeners. So can you tell us what you think the best advice is that you have ever received?
I think the best advice is actually to pursue an area that you like, because you'll put more effort into something you like to do. If it excites you, it's probably an area you'll do well in. So concentrate on not where you think you'll get a job, but where you think you'll enjoy your life if you do that. And also stay humble. Just realize that whatever you understand, whatever you study, it's only scratching the surface. You got a lot more down there. Things are going to change. And you're just an observer in the museum. You're not a creator. So just enjoy what you find.
Wonderful advice, Charles. Is there any other last piece of advice or any last inspirational note you would like to end on for this interview?
Well, yeah, I just realized that you're here to study nature, not to change it. You're here to appreciate what we see around us, not to create it. I mean, we're only here as observers in this journey, and I think it's a great journey, and we should enjoy every step along the way. Don't worry about the destination. It'll take care of itself. Just enjoy the journey.
Wonderful note to end on, Charles. Enjoy the process. Enjoy the journey, listeners.
That's right, yeah.
Now, Charles, can you tell our listeners how they can reach out if they want to learn more about you or your work?
They can contact me by email. I'll be happy to spend time talking to them about any problem they want. They could even call me by telephone if they like, but I think email is the most convenient way. So send me an email note, and I'll be happy to respond to it. It's CMH for Charles Morris Hohenberg, CMH at WUSTL.edu. That's for Washington University St. Louis.edu. WUSTL.edu. That will get to me.
Wonderful. Well, Charles, we appreciate it. And thank you so much for joining us today and sharing your story.
Thank you, Marie. I enjoyed talking to you.
This was a pleasure for me. And thank you, listeners out there. We'll see you next time on another episode of People Behind the Science. Your voyage to the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to seeing you next time on People Behind the Science.